Hello everyone. This video will present the examination of a natural ventilation system. To be specific, different types of wind catchers will be added to a building to analyze their impact on it. Several scenarios have been designed to assess their probability of success. But before getting into the details of this study, what is a wind catcher? A wind catcher is an architectural structure used for many centuries, originated from the ancient Persians and many Middle Eastern countries to create natural ventilation in buildings. The function of this tower is to catch cooler breeze that prevail at a higher level above the ground and to direct it into the interior of the buildings. Moving on to the site analysis, my building is located in Los Angeles, United States. This is a 3D model that I created for my building, which serves as a car showroom to allow maximum visualization. This two-story building has a curtain wall front facade to allow car display. Let me take you through the main surroundings of my building. On the north side, residential neighborhoods which are characterized by their high density can be found, while on the east side, Los Angeles International Airport is located. Lastly, on the western side of my building, the ocean can be found. The location was precisely chosen to be located in a high-density area with several facilities around to facilitate car rental or purchase to many people. While analyzing the weather data of Los Angeles, it is found that the average temperature in summer is around 29 degrees Celsius, while in winter, the average temperature is 8 degrees Celsius. As for the wind direction, most wind comes from the west direction and southwest, which in later stages guided me in placing the openings of the wind catcher. According to the ASHRAE standards, 2011, the comfort temperature is obtained within 19 to 27 degrees Celsius. The building certification system used in the US is LEED, which I used on my building, in which the minimum standards were applied for material selection and U value. I used concrete flooring with epoxy coating with a U value of 0.2. As for the roof, thermoplastic single-ply roofing was used with a U value of 0.14. Concrete external walls with a U value of 0.4 was used. Lastly, the U value used for glazing is 1.6. Before getting into the investigation of the natural ventilation system on my building, I would like to briefly explain my simulation matrix. I used a cumulative investigation path in which I started with the base case that will have the HVAC on all year. Then, the HVAC will be turned off in the 3 months of summer, which are July, August, and September, to examine if the wind catcher will succeed or fail as a natural ventilation system without the use of AC. I will create 3 different scenarios for the wind catcher, in which the best of them will continue for further investigation. Then 3 different scenarios will be created by keeping the variable of the winning scenario as a base, and so on, till I reach a total number of 9 scenarios, in which the best will be identified by the end. As for the simulation conditions, I created weekly and annual templates that displayed working hours and days where HVAC and electricity are turned on. As for the boundary condition, it is fixed to the 18th of August in all simulations to run the CFD on, to have reliable results. This day was chosen because it's the day with the highest wind speed in summer and to get maximum results. After examining all 8 directions, it was found that the north is the optimum orientation in terms of shading and total energy. Starting off with the base case shows high energy consumption as the HVAC is continuously on. The energy consumption has a total of 258 megawatt hour. The graph shows the high energy consumption, especially in summer. The internal temperature of the building is consistent, with an average of 26 degrees Celsius. as well as pressure that is static, which reflected on the velocity simulation that shows very limited airflow internally. The pressure simulation shows the difference in pressure around the building envelope, creating turbulence even in areas with low velocity such as the one represented by blue arrows. Starting with the natural ventilation scenarios, HVAC will be turned off only in the 3 months of summer to investigate its influence on the building. The first 3 scenarios examine 3 different heights, which are 4.5, 6.5, and 8.5, in which they are based on the literature. According to the literature, the higher the wind catcher, the better performance it has. In my study, the results show that among the 3 wind catchers, the highest one has the lowest energy consumption, which is 214 megawatt hour, and low air temperature with the mean of 26.7 degrees, which shows that my results align with the literature. Simulation shows how the air temperature throughout the building is within the average of 26 degrees, and that the building and wind catcher shape create high pressure that directs the air into the building, which is obvious in the velocity simulation. The external velocity simulation shows how the wind catcher is exposed to the high wind speed. Moving on to the next set of scenarios, I kept the optimum height and examined different widths based on the literature too. The literature also states that the wider the wind catcher, the better performance it has. Analyzing my results, the widest wind catcher has the lowest energy consumption, which is 213.8 megawatt hour, and has the lowest air temperature that reached 26.4. Notice that these results are also lower than the previous scenarios. The simulation shows how there is a slight change in temperature and how it enters the wind catcher in higher degrees and gets cooler by the time it reaches the floor. Velocity vectors here display the airflow and how it's directed into the wind catcher and then into the building. Using the optimum height and width, I moved to the last 3 scenarios, where I examined different types of openings. I used 2-sided, 4-sided with smaller divisions, and 4-sided with wide openings. It is stated that the 4-sided works best in many cases, and in my case, the 4-sided was the best. The 4-sided wind catcher has also the lowest consumption of energy, which is 213 megawatt hour, and air temperature that reached 25 degrees Celsius. It is clear in the simulation how the temperature is cooler in comparison to other scenarios, and how the high pressure around the wind catcher is creating high velocity. To conclude, my experiment is successful in terms of energy savings, as it saved 45 megawatt hour from the original energy consumption in the base case. Also, the air temperature using the wind catcher in summer is in the range of 25 degrees, which is within the comfort range according to ASHRAE. That means it is valid to be used in summer in Los Angeles. In addition to the successful natural ventilation system, smart building technologies are added to the building automation system of my structure. A temperature sensor is added to the BMS to allow it to open or close openings of the wind catcher according to the temperature. Also, the HVAC is linked to the openings to turn it off whenever windows are open. Daylight sensor is installed to allow the BMS to control artificial lighting when not needed. An occupancy sensor was placed to determine the areas that are not frequently used. Also, the BMS will be programmed to close all gates in after hours and turn on the security system to ensure the safety of the building. Finally, to reduce the energy consumption, all auxiliary machines will be automatically turned to low consumption mode when not in use. In addition, the BMS will be monitoring all smart meters such as electricity meters, HVAC link to electricity meter, and smart water meter to analyze consumption and building performance, as well as detecting any abnormalities and defects.